Welcome to Workshop Metal Forming Part 2. Now, we're going to start this workshop off with discussing bending tubing, because you will be bending a lot of tubing. You will be bending half-inch tubing for the half-scale car, and you'll be bending 1-inch tubing for the full-size car. Now, this is our tubing bender for 1-inch tubing. I'm going to show you basically quickly how it operates. I also have the half-inch tubing behind me, and I will show you how that operates. But first, let's talk about what happens when a tube is bent. Now here we have simple two-corner bends, 90 degrees. But if you look closely at this one, you'll see rippling on the inside of the turn. There are corrugations there. Now that's caused from a couple of things. One, the tube is too thin and or a little bit too hard to form smoothly. Also, if the shoe, the mandrel shoe here that guides the tubing and keeps its shape, if it is sticky, if the tubing's rusty, if there's a lot of friction going through, it'll create more drag, more heat, and that can cause some deformation. But chances are this is just a very thin tube. Thin tubing is more difficult to bend smoothly because the metal on the outside of the turn has to stretch. The metal on the inside of the turn has to compress. So you're stretching metal and you're trying to compress on the inside and stretch on the outside. If the tube's very thin, there's not enough metal to spread all those forces out so it concentrates. Now, solid bar is very easy to bend because there's plenty of metal to distribute out the forces. Now, I will pick up a thicker tube. Well, this is a little thicker tube, and you can see the inside of this turn is much smoother. This metal is a little thicker, and here I have a very thick tube. And it's just as smooth as it can be. Look at the wall thickness on this one versus this one. Thin tubing is more difficult to get a smooth bend in. There are some tricks that can be done. Heating won't help. Heating can actually aggravate it at times. What's usually is done on very thin wall tubing that must be bent is that you can fill the tube with dry sand and cap the ends. The sand inside will help support the walls and distribute the forces. It'll help, but it won't take care of every possibility, especially if the tube bend is extreme. Factories have, in order to do specialty work bending very thin tubes, actually fill the tube with a soft metal like lead or tin or solder, which is a tin lead, and then they heat the tube and melt out the soft low temperature. Talk about hardness. Steel, of course, is a tough material, but you can get steel that's been hardened, and if you try to bend it, it just won't bend. It'd tear the machine up because it would be super hard. You can have half hard, you can have soft. That's also true of non-ferrous metals like aluminum and copper. I'll pick up an example of those metals. Here we have a copper half-inch tube. It comes in a roll and it's soft. But the more you move it around, the more the molecules are stressed and the more heat's created, and that's what you get. After a while, rather than a nice smooth bend, the metal hardens and you try to bend it, it can't stretch anymore because it's cold work, and it flattens and kinks. And that's not what you want, because that pinches off. So the metal has to stretch on the outside of the turn and has to compress on the inside. Now here I have a hand bender with a piece of aluminum. This is soft aluminum. It should bend nicely. This is a simple little hand bender. The tubing fits in like so. You have a little hook that grabs the tube. This is the shoe that guides the bend in the metal. So you stick it in like this. We'll bend this by hand. Click over the hook, bring this back around, and we'll guide this up in line. And I should be able to force that around. And this is a nice soft aluminum, so I should be able to bend this, yes. That's bending. Have to be Arnold Schwarzenegger to bend it, but here again, the metal was too thin. It did bend, it didn't collapse like the copper did, but if you look, the outside did flatten somewhat because the wall thickness is just not thick enough to provide the metal to make a nice, smooth, even 90-degree bend. So if that's the case, you may have to do a large radius and do a series of smaller bends to get it to go around a corner rather than one really tight bend. That's one little trick. Now, this little hand bender is fine for copper and aluminum. It's worthless for steel. Steel's just too strong, even the softer grades of steel. For steel, and this is what you will be using for your half-scale model, you will build. We have a steel half-inch tubing bender that has a rack and pinion drive system, so you have a lot of mechanical advantage. So you have the same little hook to engage the tube. Here's a piece of scrap that was just lying about, so I will back this up. I'll engage the hook. Now you see the wheel, there's a gear down here. Let's see, we'll bend it that way, hopefully. Is that going to work? Okay, got it in the guide shoe here, and then the other shoe. And here we go. Now, normally I would clamp this in a vise, but I'm doing it for purposes of illustration. But I have a lot of mechanical advantage because I have a gear drive here. And I'm bending a steel tube, which is many times tougher and more resilient than aluminum or copper will ever be. So you have to have the right bender for the right job. You have to jiggle it out. Which can be an art in itself sometimes. There we go. We have a bend. No collapse, nice smooth bend. You can do that to build your half-scale model with this bender. Now, you can't bend a radius tighter than this circle describes. So if your scale model, if you need your roll hoop or a curve on the car that's tighter than this, you can't create it without cutting and sectioning. So be aware of that. So that's the half scale. That's the half-inch bender. Here we have the 1-inch bender, and I'm going to show you how to stick a piece of tubing in it and work. Here's our graduated scale. It's free to move around. Here's a little indicator arm, very poor one by the way. That should be improved. This part over here, it's just put over here to hold it. It fits in here like this and actually holds the tube, and these are the guide shoes here. So, what you should actually do, there's so much pressure involved in bending steel, you should use a little light grease on these parts every now and then. So all these guide parts with the tubing has to slide through. I'm going to put a little coating of grease on there. You also don't want to try to bend tubing that's rusty, dirty, covered with sand, just in general in poor condition. All you'll do is just tear up this equipment. In fact, there's some wear and tear on these guide blocks right here. We may have to replace them before long. So, being we already been working on this one, I'll show you how to load it. And I'll show you something very important about bending tubing. All right, we load it against the shoe. This is free to float up and down. We bring it all the way through until it's all the way through. Then we rotate this around like so. Now there's a pin here and a bolt. You won't be able to see it very easily. But this part here, this fits over the end of the tube. This is the hook. But notice it's not a simple hook, it's nice and fat to spread out a lot of the load. So that's the hook. And you have to jiggle it in and engage it. This is big stuff, so it takes some jiggling to get everything to line up. It may be a little sprung too. Now here's what's hard about bending tubing. Making one bend's easy because you don't have to worry about any degree angle or which way the bends are pointing on the first bend. On the second bend, yes, because you notice how these are coming out the same. So how do you do that? If I start bending this now and it's tilted like this, then the bend's going to go off and it's not going to point at this other tube. So I want the bend to point at this other tube, sort of create a ring, right? Now, how do we do that? It's very simple. We use a level. So if we're going to keep it in this plane, we put a level on it, and if the machine is level, and then we level this tube, then when we bend it, it should be on plane. Now, on tubes that have a lot of multiple series of bends, I've even welded on a flat plate on the back side to where I'd have a place, a straight edge to rest a level, so that as I move from bend to bend to bend, I could re-level the tube and keep all the bends on the same plane going around. It's a very expensive piece of tube. So you pull some pressure on it to lock it, and that's it. Now, this looks like a staircase over here. This is your ratcheting bar. That comes in on, there's a heavy arm back here. Have to re-level that, make sure, because it will slip. Normally, this is a two-person operation to do this. One person would be holding this, keeping it level. Now, this is the actual arm that you move to create the bend. And that actually bent the tube a little bit. Not very much, but a little bit. Now, that's why you have a series of teeth here. This arm comes all the way around until it can't move anymore. Then you release it, you fold it back, and you get the next tooth to engage. Okay, so I got that one. Move it back. Click, grab it again, click, grab it again, click. Now right here, I can set up my degree wheel. If I want a 30-degree bend, 45-degree, tighten the bolt under here, use this pointer so I can tell exactly how many degrees I'm getting from each subsequent bend. And you just keep going a little bit at a time. And eventually, you'll have a bend. Okay, now I've run out of teeth, so there's another pin here, and I can move it back and pick up the next hole here on this half-round shoe to get more degrees. Bring the ratcheting bar back in, bend, rehook, bend, rehook, bend, rehook, and that's all there is to this. Okay, and I got a 90-degree bend. Or if I wanted a 60-degree bend, I can tell it on this wheel with this pointer. But I advise you have a better pointer than that. That's sort of poor. Pull out your retainer. Put it over here somewhere. Put the pin in it so it won't fall and get away from you. There we go. Pull this one out. Disassemble. And there we have a 90-degree bend, and it's pointed at the other tube. It's not running off to one side severely. And that's how you do that. Use a level to keep everything on the same plane. If you want to create a different plane, but notice this is that old very thin tubing, doesn't handle well. Notice how it flattened. And it's just going to do that unless something's put inside to support it. This tubing's too thin to be bent properly. But it's okay to practice with. Now, if you're using extremely heavy tubing like this is roll bar tubing, then you're not going to be able to bend this by hand. That's what this red piece of square tubing is for. It slips on the end, provides additional leverage. That's for bending the really heavy stuff. And so we keep this with the unit. And that's basically it for bending tubes. You're stretching the metal on the outside, you're compressing it on the inside. And you're not collapsing the tube, hopefully, and you're making it line up to where you want to go. So go do your project. All right, now here we are in the sheet metal workshop, where before we were in the tubing workshop bending tubes. And as I discussed, tubes, when we bend them, they have to create a compound curve because they're curved in a cylinder, and then we're bending the cylinder. That's metal curving in two directions. When we start dealing with sheet metal and we get beyond simple just curved shapes and we want to curve the metal in two directions at once, that's a compound curve, and that's a whole new ball game. And I'm going to show you the basic grassroots way of actually creating compound curves in sheet metal. Now, just like the tubing, where you have full hard tubing, half hard tubing, and soft tubing, same way in sheet metal. And we cannot create curves, compound curves, in fully hard sheet metal. We have to have at most half hard, preferred soft, because it's malleable and it gives us the ability to stretch and compress and do what we need it to do to give us the shape that we want. It's 10 times easier to stretch metal than it is to compress it, especially with rudimentary shop tools. So I'm going to show you how to do that. So I had my little paper template, put it on some sheet metal, use the shears, cut out a little elliptical disc, rough shape, not precision measured. And this is only 1/2 millimeter thick, 0.20, no, 0.020. This is 3000 series aluminum, and it's soft. Now, when metal's stretched, it gets thinner. That's where the shape comes from. The base metal is made thinner and thinner. So I'm starting with a very thin piece. I don't have a lot to work with. If I was going to do something like a car fender or a very complicated, deeply drawn shape, something like here, something that's deeply drawn, metal's been forced. This was done in a stamping die at a factory. Just a way to stretch metal is with a hammer, a mallet. This is a teardrop mallet. It's got a big rounded end on this end, small rounded end on this end for getting into tighter places. And guess what? Leather sandbag full of sand or steel shot, or used to use lead shot, used to be real popular. It has to be full of something soft that will give with a hammer blow, but not so firm that it dents the metal severely and tears it to pieces. So this would allow us to shape with the hammer and stretch it. And what I'm going to do is I'm going to stretch it in the center, and I'm going to create what's called a blister cover, because on a lot of vehicles you can have things that protrude out. Maybe it's a hydraulic filler cap or something like that that protrudes slightly from the plane of the body of the vehicle. So you need a cover to go over it. And these are called blister panels. And they're very popular on race cars and airplanes. And they're very, very simple to do if you have the right hammer and a sandbag. So being we want to stretch the metal in the middle, I'm going to just start pounding it here in the middle. And I've got to hit it hard enough to where the metal gives and stretches. So here we go. And if it's a small piece, it's a good idea to hold the edge with some pliers so you don't smash your finger and fingernail. You see the sandbag giving, creating a depression, and that's exactly what I want. And I can just keep working this until I get the approximate shape that I think I need. Now I'm reversing it to the small end because I'm going around to create a perimeter form. This takes patience and a little bit of practice, but not an extreme amount. Now, if the depression in the bag gets too deep, you just refluff the bag. Move the sand back in there, build it back up, and here we go again. So, there we are. If you can see, I'm really forcing the metal to move into a crown. Now, okay, so we have a nice smooth crown, relatively speaking, and I want to get a nice soft hammer. I'll use my little plastic hammer because it's the least marring. And now I'm going to come over here to a nice flat surface like on our little anvil, and I'm going to try to create a flange that goes around the perimeter. So all I'm doing is just flattening it out. Now the metal's getting stiffer and stiffer the more I work it with a hammer. So that's why we want to start with very soft metal, because if the metal gets too stiff and brittle from the hammering, it will start cracking and we won't have a part. So I just go around the perimeter one time, create a general shape that I know I need, which is a perimeter. Now, Smith, which I am, by the way, is a worker in metal. So you had goldsmith, silversmith, and they basically were artisans that would spend hour after hour tapping metal until it's in beautiful shapes, beautiful silver serving sets. And believe it or not, they started out just this rough. And you have a big hammer, makes big dents. Smaller hammers make smaller dents. If you get down small enough to this size, now you get very, very tiny dents. And if you have enough thickness of metal left, you can actually just use sandpaper to sand out any remaining marks that might remain. And you just keep going and going and going and going, making big dents into smaller dents, into smaller dents, and into smaller dents. And you work it against certain shapes until you're satisfied with the result, which would be a little blister cover. It sits flat, or if you want to recurve it to go on a curved surface, that's fine too. But that is a little blister. And as you can see, it protrudes, and the flange has been hammered back down smoothly. You can file the edges to get them straight and square and attach this with screws or rivets, and you have a blister cover. If you cut this in half with a saw, you would have, let's see if I have one already made. I believe I do. Yes. If you cut this in half, you would have a scoop. A nice small scoop to vent a battery, vent a hydraulic reservoir, provide, if you turn it around, it's a scoop if it's facing forward to the motion of the air. If you turn it around, it's an exhaust port. So if you had a fuel drain from any spillage or any kind of overboard draining system, you can streamline, rather than have a coarse little tube sticking out the bottom of your vehicle, you can have it come through a little hole and cover it with one of these, and you have a nice streamlined little drain fixture, so that as the airflow comes by and any hydraulic fluid, oil, whatever overboard fluid you're trying to dump could come out and it would all be streamlined. Makes for a very nice finished product. And as you see, it is much smoother now that I worked it with a smaller hammer. If you have, you can just keep going with it until you can get it as smooth as this one. This one. So the more effort you put into it, the finer the product you get. Now, like I say, curving in 3 dimensions is what's required to get aerodynamic shapes. A simple 2-dimensional curve is fine, but it basically gives you a slab-sided vehicle. Now, if we look over here at this picture of this World War II airplane, you'll see just how many components on this aircraft were compound curved. These are engine cowling panels here. And if you notice, they come forward and they curve in toward the propeller spinner, but they also are curving this arc at the same time. So that's a compound curve. If you look here, here's our little scoop, larger for that opening. Here, more scoops. And if you look at the fuselage body here, notice that in the x-axis, left to right, it's virtually a teardrop shape coming this way, and also it's sloping down from the windshield also down to this point down here. So it's curving in the y-axis and curving in the x-axis, and so it's curving in 2 directions at once. Now, if you've got a big enough sandbag and you need a big panel that curves in 2 directions at once, you can do it with a hand hammer and a sandbag, but that requires a really big sandbag. There's a better way to do it, and that better way is this machine right here. This is called an English wheel, and it is for metal forming panels, larger panels. These are a little bit too small to work in an English wheel, but if you had a panel, an engine cover panel here, a nose panel, a wing panel, something that had size but required curving in 2 directions, it's actually called belly, is that you can start with a flat piece of sheet metal and you actually pooch it out in the stretch position and you create a belly to this sheet metal panel. So you measure out your panel with a paper template or something like that, and then you have a frame that you can check it against, and then you can work it in this machine to create the 3-dimensional stretch, the belly that you need. Now, we won't take the time to do that in its entirety in this machine because it can take a long period of time. But here we have a piece of mild steel. Now here again, this machine only does sheet metal, and it only does soft sheet metal, and you can't put in a piece of 1/4-inch steel or 1/4-inch aluminum that's very stiff and expect it to do anything in this machine. If you tighten this wheel, this is how you tighten the work in the machine. This piece is a little bit rusty. I don't want to put it on the wheels and damage the wheels. Let me find something that's a little cleaner to use. Okay, we'll use aluminum. Now, this is the anvil wheel, just like the working part here. On the blacksmith anvil, this is the anvil wheel. This is a screw thread. This raises the roller wheel. You could think of this as your hammer. This raises it up and we preload the work. Now notice, let's see how flat this is, and it has absolutely no belly to it, no 3-dimensional stretch. So we load it in the machine, we bring it in until we get a slight pinch, and then we lock this. This keeps this from creeping back on us. Now there's a preload, and if you can see the egg shape to the roller, we have several rollers in here, and some have less crown than this working wheel does underneath. This is the most severe, so it works the fastest for the tightest radii. So all we have to do is preload it slightly. Now you cannot just crank down on this thing. It will spring the machine and damage it. You only need light working pressure, and the way you work it, you move this back and forth, back and forth, back and forth, and just like my hammer was stretching the center of that small panel, this wheel is stretching the metal. It's actually compressing it, causing it to get thinner. It's got to go somewhere, so it goes into a curve. The outside is not being stressed, so it's trapping the metal in the middle. So I'm just going to keep working this around gently. I'm not going to force it. I'm just moving slowly. I don't know if you can see that, but you can see the streak marks in the panel. That's where the pressure from the crowned wheel is forcing the metal to stretch. Now, one thing you have to watch when working with an English wheel is that there's a lot of mass in this anvil rotor, and you can get some momentum going. And if you get sloppy and allow your thumb to come over here and be pulled in it with inertia, travels into that wheel, it will give you a blood blister under your fingernail, and it hurts like the dickens. So try to keep your fingers and hands to the side, and take your time, and you just work the metal. You can actually draw on here with a marking pen a pattern, and you can just keep racetracking that same pattern. Now, release the work. Now, as you can see the belly that's been created, the curve. That before this was a flat piece of metal, but now it's been stretched in the middle, and it has created some shape to it. It's easier to shape in this axis than in this axis, but it can also be bent in this axis slightly. Just have to keep working it crossways to the direction you want it to curve. If I want it to curve this way, then I work with the wheel this way. Back and forth, forth and back, back and forth, forth and back. Now, I also wanted it to curve this way because when you look on the airplane, we're curving in two directions at once. The primary curve is this way. A shallow curve is this way. So we would actually take this, we would work it a little bit. We would go, if we were making a replacement part for that antique aircraft, we would actually take this. I've done this many times, and we take it and we fit it on the plane, and we just keep bending it until it lays down against the aircraft exactly like it should. And you're done. Then you trim the edge. You cut the outline, put your holes in it for your fasteners, and that's it. It just takes patience and a little common sense. Now here you can see this working wheel here. I'm going to lift out one with less crown. So as you can see, this one has less crown than this one. I have a whole series of them. We have 5, 6, 7 total. The last one is completely flat, so we have a flat wheel against a flat wheel. If you have some dents, like right here, this old piece of metal here has some dented place. If you put a flat wheel against a flat wheel and run across there, it'll flatten those down just like using a hammer. So you select the roller wheel depending on the size of the panel. If you're working a small panel, use a very high crown wheel. If you need very little curvature, you use a working wheel, a dolly wheel that has less curvature. You just match the work to what you need. It takes a little practice, but that's all there is to the English wheel. The main thing with the English wheel, keep it clean. Don't use dirty metal that will damage these rollers by grit and metal shavings going through there. Make sure the metal's clean. Make sure these have a little oil on them, and do not overcrank them, because you can spring this frame if you just get ridiculous with the pressure in order to try to go faster. It's better to take your time and do it right. If you overstretch the metal, it's 10 times harder to compress it back. Sometimes you can't compress it back. So it's best to ease into it by slowly stretching until you get what you need. And that's all there is to it. The rest is practice. All right, so we've used our English wheel. We've created a panel with a belly to three-dimensional shape. Now, I'm going to show you how to do something that's very, very nice. It creates the professional, high-quality edge fit that you may have wondered, how in the world do they do that? They get the edges of the sheet metal to come out so evenly, because normally if you just have one panel and then you put another piece of metal on top of it, let me turn that over, I got a piece of steel, a piece of aluminum, then this is a shingle lap. You overlap it and then you come down through with some kind of fastener, screws, rivets, Zeus fasteners, whatever. But you see here that this piece is riding on top of this one. And it has a step or a shingle lap joint. This is the way the shingles on a house work, is that you put on the lower shingle first, then you put on the next one and overlap it, so the rain coming downhill comes off, drips off this edge, hits this edge, and continues going down. This works on airplanes too, or race cars. If the airflow is coming down from my right to my left, then it will come down here and flow down. What you don't want to do is lap it like this, because if there's any pooch, then the air can get under it and try to lift this panel off and blow it away. Now, this is a simple joint. I'm going to show you a more sophisticated joint and how to make it. This is a rolled, jogged edge. Now, as you can see, it comes over here, and then the metal's been moved down, and the thing has been jogged offset. So, if I have this part here, and I put another piece, I can get virtually a seamless, no step joint, because this sheet metal, if it's the correct thickness, and the machine that forms this edge, if it's set correctly, depending on thickness, you can get virtually a stepless joint. And it forms the easiest thing in the world. This machine is what's called a bead roller, or a just simple crank roller. It has these die wheels here. They're made with certain shapes, and as you can see, this is the jog and this is the offset. If I take a little piece of metal and put it through here, I'll take our little belly, and if I put it through here, and this is hand cranked, it's actually best to have two people doing this. I'm going to try to do it myself. Now, I won't be able to get it as perfectly straight because I'm cranking and I'm trying to guide at the same time. But as you see, we formed that jogged edge, so if another piece of sheet metal lays in here now, we can have a nice, virtually stepless joint. Now, that's one thing that this machine will do, and it's adjustable. These rollers can move up and down to accommodate different thickness, and it takes a little trial and error to get it just right. But when you get it just right, it'll stay there, and you can do piece after piece after piece. You can also go cross end and do a panel all the way around. There, I didn't run it quite as straight, but you get the idea. Now, on that little step right there, we just hammer form down that little overlap there, and now we can have a panel that would fit on the side of an engine, and other pieces of metal can lap to it, and that creates that little stepped edge. Creates a perfect seamless joint. Works beautiful on the race cars for making panels. Gives a very, very professional finish, and it's easy to do. Now, if I change these rollers and put a different roller on there that has a different shape, you can create, now these are, if you look at these, I will put something up here for contrast. Yeah. Now here, rather than a simple jog, there was a radius curve. See it round? And I passed the metal through the roller several times. I can use up to 18 inches on one side, so I could do a piece almost 3 feet wide through here by turning it around. Now what this does is, if you have a great big panel and it's unsupported in the middle, then the middle of the panel, in the wind or in the vibration, whatever, it will move in and out, it will breathe, it will, because there's no real stiffness. Sheet metal just flops around. It's like a Coke can or something like that. It just crinkles and pops and everything. But if you form these beads in the center of the panel, then it will stiffen the panel and give it rigidity without adding weight. Very, very neat trick. You can actually use them for decorative art. I've seen people actually do Roman numerals or do artistic patterns with these things, do chevrons or do series of long, short, long, short, long, short, and for decoration. And it works extremely well on belly panels. Any large sheet metal areas is to form a bead with one of these rolling machines. So if you want to take the time, we take a minute or two to change it. All right, now I've showed you the little bead roll leftover scrap I had here. Now we'll use our little panel that we made in the English wheel, being we've used it for everything else, and I'll form some beads. I've changed the rollers over here. They have the half round ones on. And what I'll do is I'll come up this one, turn around and come back. And as you see, this is steel because I haven't created very much of a belly on it yet. It's not that rigid in this direction. In fact, if I hold it up here, it's not rigid enough to even keep this little plastic hammer. So it should be rigid enough when I get done. Proof of concept here. So basically all we're going to do, like I say, if I had a helper, this would be much easier. So I'm just going to slowly down here. Now I can as I turning the wheel, I can actually turn the work. Make a semicircle. There it is on that side. That will give a large panel the structural rigidity it needs to keep from flapping. Doesn't add any weight, and if you're very neat with the way you do it, it can be very attractive. That's rolling, using a rolling bead former. Simple machine. This is my machine, by the way. I'm loaning it to UCI, the Formula One guys, to use, but please don't abuse it. It can be damaged like anything else if you don't take patience with this kind of stuff. And I'd be glad to help you operate this. It's very simple, and there's just 2 bolts back here that can be released that allow these to open and close, so you can set them to different length metals. One person to operate it, one person to feed the material in and guide it. That's all you need. If you want a really, really straight line, you can set up a guide, some sort of piece of metal or board or something here, so that it controls the edge as it goes through, and you'd have a perfectly straight bead line like it came out of some $1 million machine. And that's all there is to bead form rolling.